Prospect Lab. You're also traveling from South Korea?
Yes.
Wow. CEO and founder of Prospect Lab.
Yes.
Korea based technology company specializing in BIM and digital twin platforms.
Yes. Good afternoon. I am Gutek Kim, CEO of Prospect Lab in Korea. It's a great honor to join the second ADIF workshop. Today I will present a case study of BIM-Based digital twin for integrated airport facility management developed with Korea Airports Corporation, and then share our joint research with Texas A&M University and Yonsei University on AI-driven automated quality checking. Our company develops BIM solutions. We have an in-house BIM GIS visualization engine along with technologies for automated BIM quality checking and AI-based design automation. There are 15 airports in Korea, and 14 of them are managed by the Korea Airports Corporation. The case I will present today focuses on Gimpo International Airport in Seoul. Gimpo Airport began its digital transformation in 2020 by building a BIM-based digital twin. The digital twin of Gimpo Airport covers the airport and approximately 15 kilometers of its surrounding area. All the facilities shown in this video are modeled in BIM and visualized within an integrated environment. As you can see, even the fine details of the facilities and terrain are accurately reproduced to reflect real-world conditions. Such accurate reproduction of real facilities in the digital twin enables 3D visualization-based monitoring, prediction, and operation of assets. Simulations that are difficult or impossible to perform in a real airport can be carried out safely within the digital twin. KAC has built a system called KAC BIM, which is used for the integrated management and operation of airport facilities. The digital twin developed by KAC is built on BIM technology. Individual elements such as walls, floors, and ceilings are modeled as separate objects, each linked with detailed attribute information. As you can see, even highly detailed components, such as fire extinguishers, are precisely represented, and this information is widely used for facility operation and maintenance. What's important is that each object is accurately linked with its management-related data, including names, codes, and classification information. Even a small sprinkler contains its associated metadata within the model. Here, the architectural elements are hidden to reveal the electrical, mechanical, and plumbing systems. This single model alone contains over 2 million objects. The 3D model allows users to cut cross-sections to examine detailed interior information of specific area, review floor plans, or selectively inspect the 3D geometry of desired spaces. When geometry and attribute information are combined and managed in an integrated manner, it becomes much easier to quickly locate and utilize up-to-date facility data. And it also provides a powerful basis for effective problem analysis. For example, if a problem occurs in a ceiling duct, the manager can quickly trace its path and identify which equipment is connected to. They can also easily determine what kind of repair is required and review the specifications of related components through the attribute data. If a press pump needs replacement, the related piping connections can be visually identified allowing the operator to anticipate which parts may be affected in advance. The digital twin can be linked with the existing risk management system and used effectively for space management of facilities. In airports, a large number of retail stores and office spaces are leased out, which requires systematic management. When lease data is integrated into the digital twin, management efficiency is greatly improved, as it is based on accurate location and area information, as you can see here. Equipment specs, inspection histories, and repair records are integrated with the 3D model. Selecting an object or space reveals all related maintenance information, enabling effective inspections and operations. We also support inspections using tablets, AR, and VR. It also runs on Microsoft HoloLens or Oculus and so on, though these devices are not yet widely used on site. Please excuse the blood parts for security reasons to the airport runway. The screen you see here shows real-time aircraft movements visualized within the digital twin. The yellow arrows indicate real-time wind direction and speed data provided by the meteorological office. The system enables tracking and recording of aircraft positions and provides instant access to flight information. When applied in the control tower, it can support more accurate and efficient air traffic control. Unlike conventional systems, the digital twin visualizes the precise shape, orientation, and position of each aircraft, significantly enhancing safety and accident prevention. As flight movement data accumulates, it can be effectively utilized for accident analysis, flight path simulation, issue diagnostics, and even controller training. We integrate the real-time noise maps and data from fixed monitoring stations into the digital twin for visualization and analysis. This scene shows a simulation of height restrictions around the airport. As you can see, any violations of height restrictions can be immediately identified through visual feedback within the model. The system can be expanded for multiple purposes, such as design review and compliance analysis. It can also be integrated with aircraft flight paths to monitor altitude changes during takeoff and landing. Future infrastructure, such as UAM vertiports, can also be simulated within the digital twin environment. UAM flight operations can be visualized along with their surrounding environment, enabling real-time monitoring and air traffic management. In the future, all urban information will be integrated and managed within digital twin platforms like this. At Gimpo Airport, a passenger flow system has been installed using LiDAR sensors to track passenger movement within the terminal. This data is visualized on the digital twin to monitor and manage passenger congestion in real time. Privacy-safe avatar visualization can also be shared with passengers, allowing them to see real-time crowd levels and navigate the airport more effectively. The system changes colors according to congestion levels in each zone, allowing operators to identify crowded areas and take appropriate actions. The screen you see here shows the snow removal vehicle monitoring view. In the past, it was difficult for the control center to visually identify the working areas of snow removal vehicles. But this issue has been resolved through the implementation of a digital twin. This system is a great example of how an internal engineer's idea was turned into reality, demonstrating the diverse possibilities that digital twin technology can bring to facility operations. This video shows the visualization of bird movement patterns within the digital twin environment. Currently, air traffic controllers in the control tower cannot view bird movement information in 3 dimensions and can only identify approximate positions on a 2D map. As a result, controllers cannot provide controllers can only provide limited assistance to pilots, such as indicating the general direction of bird movement. Through 3D visualization based on a digital twin, far more effective and proactive air traffic control will become possible. If digital twin technology is fully implemented, it will open up possibilities we can hardly imagine today. And it will truly revolutionize the way airports are operated in the future. As AI and robotics became mainstream, their data and logic will be integrated and managed via digital twins. KAC is extending its integrated management system toward a physical AI platform for AI simulation and on-site application. We believe similar BIM-based digital twins are needed in the plant sector as well. Next, I'd like to introduce part of our ongoing joint research with Yonsei and TAMU, the development of an automated quality checking system for BIM models. The successful development and implementation of the digital twin-based integrated management system, as I presented earlier, was made possible largely through the adoption of this quality checking technology. For an integrated facility model to be used effectively, each component must contain the appropriate information required for operation and management. For example, to manage spatial and leasing information, each space must have the correct space code entered into the model so that it can be linked with the ERP's contract information. As you have seen earlier, complex facilities consist of millions of objects, making it practically impossible to manually verify the consistency and accuracy of all information. For our research, we are using 2 BIM models. One is a BIM model of a food waste treatment facility, and the second is the TAMU facility, which was model re-engineered with laser scanning. The first one, the first type of the automated quality checking is a property-based checking. It is a very simple one, so go to the next. The next type is quality checking analysis both the location and properties of the object. So the pipes, which is located on the pipe rack, it should be at least 50 millimeters. The kind of things can be automatically checked with the technology. And the next type of quality check verifies information based on the type of space in which each object is located. For example, when insulation is required on pipes or equipment to protect workers, the system needs to determine whether the space combining the object is accessible to humans. But it is difficult to determine the space is whether a space is actually accessible to people. So the system automatically, using AI technology, system automatically checking the space's classification code. System infers the classification code and which room is accessible to human. So combining this information, the system is checking the kind of rules. Yes, and object connection check, the hood and the ventilation system is connected to pipe. The last one is AI-based rule set modification and generation. Using LLM model, the system can generate or modify the rule sets using the chatbot system. So using natural language, you can create a new rule set or modify the rule set is possible. And through this Yonsei and Tamil, through this collaboration, our goal is to establish an open and interoperable digital twin framework that bridges design and operation, enabling a more intelligent and sustainable facility management environment. Thank you.